Let's talk about air filters and more specifically, the ability of a filter to filter out a virus like the SARS-CoV-2 virus that causes COVID-19. And we basically want to look to see evidence that demonstrates that filters are in fact capable of removing the small aerosol and droplets that contain viruses from our respiration, and to see how effectively they're able to do that. So here's a collection of filters. You can get 2-inch thick filters, 4-inch thick, 1-inch thick. You can get like this pink one, special chemical absorbing type filters. And then you can get different ranges from MERV 8 to MERV 11, MERV 16. MERV 16 is quite similar from test data to a HEPA. So when you think about HEPA versus MERV ratings, when you get to about a MERV 16 and the HEPA, you're at about the same level of particle removal. And then this chart shows how for the MERV ratings that a MERV filter needs to have a higher percentage in these E1, E2, E3 particulate size categories in order to attain a particular MERV rating. And when we think of a virus, we typically want to think of the E1 and E2 rating, the E1 being more similar with the small size particulates and droplets of what's coming out of the lower respiratory tract, the droplets that we definitely cannot see but are very, very plentiful in our breathing, whether it's through our nose or through our mouth. These small aerosols are coming out as we exhale. And then when we cough and sneeze and shear off larger droplets, say more in the 1, 5, 10 micron range, more of the E2, E3 category become important. So we're interested in this whole spectrum, but especially the very, very fine aerosol particles that are just coming out from our natural breathing. Probably not too many of you have a dirty filter collection like I do. I've got a few dozen. It takes months to collect a couple of filters, and especially when you periodically pull them out, weigh them, inspect them, take pictures of them, and put them back. And after a few months, depending on how dirty or not that I want to let a filter get, or the type of season when I'm interested in what type of particulates are on a filter in the fall versus the winter versus the spring or summer. And so, yeah, I know that's a little odd, but I look at filters. I'm interested in their pressure drop and how that changes, as well as what kind of stuff's on them. And an outside filter is quite a bit different than an inside filter, but every bit as important. With outside filters, we want to for sure remove outdoor particulates, whether it's smoke from a forest fire or from a neighbor's wood burning stove, or particulates from a factory or from car pollution, or just the natural dust and dirt in the air, along with a lot of the critters, bugs, spiders, molds, and pollens and things. When we look at an indoor filter, it looks quite a bit different, but every bit as dirty in its own right. And in today's reasonably well sealed, and especially highly sealed, but just today's conventional homes, most particulates inside of our homes today are generated inside from our breathing, from our shedding skin, from our abrading materials, from cooking, from dust mites and pet dander and all sorts of sources like that. And so these tend to be much finer particulates in addition to the respiratory particulates that we add to it from our breathing. And just to give you some idea of it, this particular filter over 2 months gained about zero point 0.2 ounces of dust. I mean, an imperceptible amount. Right? You could mail that somewhere with a stamp. And and the amount of particulates in that zero point 0.2 ounces, about 5 grams of dust, that was about 11 trillion particles if the particles on average were about a micron in size. And a micron is like 1/100th of the diameter of a human hair. Very, very tiny. So a lot of particulates that you might have inhaled if you hadn't filtered them, and potentially a lot of particulates that have a virus on them if there's an infectious person inside. Well, let's look at some of the evidence that we can remove viral laden as well as bacteria and other contagions with filters. These three references are good examples. The top one by Don Milton and colleagues found virus on building filters, and they actually tracked the genetic material in the virus that was on the building filters to people inside and the genetic material of the virus that they had been infected with. Okay? No ifs, ands, buts about it. Virus from the infectious persons were caught on these building filters. The second reference by Professor Brent Stevens and colleagues at Illinois Institute of Technology, just a phenomenal study, very detailed, very complex study of an apartment scale test facility in which in the red circle, there's a breathing coughing machine, what they called the cough box, and it was putting out a spectrum of aerosols similar to what we put out from our regular breathing, and it would periodically cough to put out larger droplets, more similar to those that we expel when we cough and sneeze. And then they had sampling plates and sensors to look at viral matter and droplets and aerosols throughout this apartment. And they were running a regular apartment scale ventilation system, air recirculation system. And what they found was very, very interesting. We'll take a look at that in the next slide. But this third reference, a very recent reference from a filter manufacturer, looked at in a test facility with air seeded with various types of contagion and various types of filters, the effectiveness of the filters to remove viral laden droplets. And the results show definitively, yes, a good enough MERV, and a good enough MERV is a MERV 11 or greater. So MERV 11, MERV 13, which we recommend, MERV 16, are at levels that will remove substantial fractions of viral laden aerosols and droplets. So no ifs, ands, buts about it that viral matter gets on filters and that we can remove it. But taking a closer look at Professor Stevens and colleagues' results, on the left, they would seed their cough box with both a bacteria, a non-toxic, a benign bacteria, as well as similarly benign virus, but two test subjects that they could use to look at the qualities and characteristics of a bacteria and a virus. And a bacteria you might think of as just being a bigger entity, maybe 10 times the size of a virus. And the virus being quite small and similar to the smallest of aerosol droplets, say in the range of zero point 0.1, 0.3, 0.5 microns, where a bacteria starts getting pretty large, say 1, 2, and 3 microns in comparison to the size of aerosols. And what their study showed was that when they seeded their cough box with a bacteria, the bacteria had very different droplet emission characteristics than the virus. And in fact, the larger bacteria with the emission of droplets tended to deposit quite close to their cough box. That is what we're told about 6-foot spacing and maintaining 6 feet from another person who's potentially infected. That for a bacteria, that seems like good sound advice. And further away from the cough box, the bacteria dropped down, as seen in this lower left-hand slide. But when it came to a virus, the virus did not tend to alter the droplet size spectrum significantly. And instead of having a large deposition of viral matter close to the cough box, the largest amount of viral matter occurred almost 10 feet away from the cough box. And 15, 16 feet away from the cough box, much more viral matter was found there than found within 1 to 2 feet of the cough box. That is, 6 feet doesn't do you much good. With viral laden aerosols and droplets, you need to be protected in other manners: face masks, filtration, fresh air. Now, the slides, the plots on the lower right show for the bacteria and the virus how filters can remove both of them effectively. And the most important thing about these plots over on the virus side is that when you look at the distance away from the cough box, the source of the contagion, that a MERV 8 filter and then no filter in their air recirculation system acted almost identical. That is, there is very little difference in the concentration of contagion found at different spacings from the cough breathing source with a MERV 8 and with no filter. When they went to a MERV 11 and then to a MERV 16, larger fractions of viral laden aerosols were removed. Much less viral matter was found deposited within the apartment in all spaces. And in fact, they found that the MERV 11 was removing about 85% of viral matter, and the MERV 16 was removing about 95% of viral matter. And that would lead you to believe that a MERV 13 should be somewhere in the middle, removing about 90% of viral matter. Now, one more piece of experimental evidence from our own work here at the University of Illinois. And I want to thank my colleagues in the jazz performance and over in the civil and environmental engineering departments for setting up both the performance venue as well as the instruments for collecting this very difficult to obtain data. And so we had about 25 people come in, and because the University of Illinois can test people every week, twice a week, to see whether they're infectious or not, we have a large pool of COVID safe test subjects that we could bring into this real performance venue, a bar in downtown Urbana, and set up a jazz performance with an audience. And with about 25 people total, we could see that as the number of people went up, without adding additional ventilation or filtration, carbon dioxide went up because of the respiration, and small particulates, those characteristic of respiratory droplets and aerosols. But also, there's something called the pig pen effect. That is, we have a cloud of other small particulates floating around us from chemicals we're putting off, from particulates and skin flakes coming off of us. And so these are mixed in there along with ones that are viral laden from an infectious person. So as we started this performance, as the crowd gathered, we first had no additional fresh air brought in and no recirculated filtered air. And then into the performance, we turned on an exhaust fan, which enhanced the fresh air. And what we see in the plot in the first orange bar is that carbon dioxide came down as more fresh air was added. And the zero point 0.3, in this case, diameter particulates also dropped down as we diluted them and the carbon dioxide with fresh air. Then we turned off the extra ventilation air and we switched on a recirculating air filter. And what we expected to happen happened. Carbon dioxide started going up because we didn't have sufficient fresh air, but particulate levels continued to drop because the recirculating air was removing, in this case, the very fine 0.3 micron particulates, but we have measurements from 0.3 up to 10 micron. So we have a very fine set of data that demonstrates the ability of both fresh air as well as filters to remove particulates. And then when we had both fresh air and recirculating filters on, we dropped the particulates down to a base level and maintained them there. And then the show ended. So there's absolutely no question that particulates of this scale, particulates similar to those in in our breathing, in our coughing and sneezing, that we can very effectively remove those with MERV 11, MERV 13, MERV 16 filters. Now, what about filter costs? Because a lot of you will get blowback. You'll say, we need to get the MERV 13 filter, and you'll hear, oh no, our fans can't handle it. It's going to cost us too much to blow air through that. We're going to lose capacity. Uh-uh, that ain't so. So anyone using a MERV 8, there's a California Energy Commission study that looked at filters specifically because of this point, and they found that a MERV 8 filter is just as likely to have the same pressure drop, as require the same blower power to blow air through it, as a MERV 13. The more significant factor is the quality of the filter, the number of pleats, the type of material it's made from, whether it's a 1 inch or a 2 inch or a 4 inch. A 4 inch has a lot more area that reduces the pressure drop and it will last longer with lower pressure drop. And and even though a MERV 13 will cost you maybe 50% more per filter than, say, the typical MERV 8 filter, that cost, when you cost that over the number of occupants and the time they spent in the building, it's nothing. Even compared to your lowest wage person in the building, you're talking about much less than a penny per hour per person for the additional cost of the better filters that are going to keep people healthy and reduce disease transmission. And you're also talking about much less than a penny per hour per person for the extra pressure drop in comparison to absolutely no filter, that what's a nominal filter pressure drop of about zero point 0.2 inches of water gauge pressure, that you're also talking about a very insignificant cost relative to the value of a human being.